last notes, we looked at the length and area relationship. We also looked at the length and volume relationships, and we worked out that the length and area relationship, the factor increases by the square. So if I double the length, I increase the area by a factor or a multiplier of 4, or 2 squared. If we also looked at 3D shapes, if I double the length, I'm going to increase the volume by a factor of 8, or 2 cubed. Okay, so we take that length factor and we cubed it. So if my length factor is n, the volume increases by n cubed. So if sides of a cube are all doubled, by what factor is the volume increase relative to the original cube? Well, if I take a 1 by 1 by 1 cube, I have 1 cube of volume. If I take a 2 by 2 by 2 cube, I have an 8 cube of volume. So if n equals 2, so twice the length, width, and height, that ends up with n cubed, which is 8, 8 times the volume. We have 8 times the volume change. Okay. So then if I have a rectangular prism, it's a 2 by 4 by 5 prism, and I increase it by 20%. Now it doesn't really matter if it's a prism and what the dimensions are. If I increase the measurements, the length, width, and height by 20%, the volume change is going to be 120% of the length, 120% of the width, 120% of the height, or the length factor cubed. Okay, so when I cube that length factor, I end up with a factor of 1.728. That equals 1.728 times more volume. Okay, so that length to volume relationship is whatever the length multiplier is, we need to apply that 3 times, or we take that factor n and cube it. Okay, so there's my relationship. It looks like this. If I'm going to take a length factor of x, a length of x, and I cube the factor here, I'm going to end up with n cubed more volume. If I want to take that same n factor and figure out how it affects the length multiplier, we cube root it. So same thing here. If I take the length, I can cube that factor to get the multiplier for the area, and then I can take the area factor and cube square root it to get the length factor. The factor meaning the multiplier that changes the length or area or volume. Okay, so let's apply this again. So how much does the length, width, and height of a 5 by 2 by 3 prism change if the volume increases from 30 centimeter cubed, okay, so this is a 30 centimeter cube prism, to 60 centimeter cube prism? Well, if I double the length, width, and height, that's not going to double the volume. So I've only doubled the volume. Okay, so if I want to find out, okay, so my multiplier is 2 times the volume. Okay, so if I want to go and get the length multiplier, well, if I want to go from volume to length multiplier, I have to cube root that multiplier. Okay, so I'm going to take that cube, so that doubling, and I'm going to cube root it. So the length, width, and height all have to change by a factor of 1.2, about 1.26. okay, about 1.26 times the length, width, and height. So if I took that 5 centimeters, okay, so 5 centimeters times 1.26, okay, I get 6.3 about. So I get 6.3 as my length. I'll do the same thing to 2. Okay, I'm going to end up with 2.52. And I'm going to take that 3 centimeters of height, and I'm going to end up with 3.78. Okay, so I'm using that multiplier of 1.26, okay, of the length. This is my times the length, width, and height. This should confirm my doubling of the volume from 30 to 60. So if I just work that out, 6.3 times 2.25, so 2.52 times 3.78, I get 60.01. Okay, so this it's approximately equal to the 60 centimeters cubes that I did. And the reason why it's off by a little bit is only to do with the fact that I'm not using exact value for that 1.26. Okay, so let's do another one here. This time the area decreases. Okay, my area decreases. My area multiplier is equal to 1/2. By what factor did the radius decrease by? Well, if I took half the radius, I'm only going to get a quarter of the area, so that's not quite right. So if the area multiplier is 1/2, then my length multiplier is going to be, okay, if I go back to my chart here, area to length multiplier, I square root. So my length multiplier is going to be square root 1/2. So that's going to be my length multiplier. And I'm going to end up with 0.707 times my length. Okay, so the radius decreased by about 71%. If I decrease my radius about 71%, I decrease my area by 50%. So the Eiffel Tower in Las Vegas. So they have an Eiffel Tower that's exactly 50% the real Eiffel Tower in Paris. Okay, so I've got an Eiffel Tower. I don't know what that looks like. I can't really draw an Eiffel Tower. I'm going to try. Okay, so the Eiffel Tower, the real Eiffel Tower uses 7,000 tons to construct. How much iron would have been needed to construct the Las Vegas version? Well, to figure that out, I need to figure out how much volume is the difference in volume. So if my length, if it's 50% as tall, it's also 50% as wide, it's 50% as long. Okay, so my length multiplier is 1/2. So if my length multiplier is 1/2, what is my volume multiplier? Well, if I go back to my chart again here, my length multiplier to volume, I have to cube it. So I'm going to take that 1/2 and I'm going to cube it. And I'm going to have exactly 1/8 the volume. Okay, so then if I want to figure out how many tons of iron is needed to construct the smaller Las Vegas tower, then I would just take my 7,000 tons my 7,000 tons, and times it by my multiplier of 1/8. So 7,000 divided by 8 ends up being 875 tons.